In this section, we will learn how to find derivatives for many functions without going through the limit process every time. This is sometimes a favorite section of students learning calculus because it just feels like we get to do things in a much more efficient way than we have been so far. So the first theorem says the derivative of a constant function is 0. And so if we've got a function that's just a horizontal line, then its derivative is going to be 0. And for a proof, let's just do a picture first, and then we can go through the limit definition. But if we have a function that's at a fixed c value, we can see that the tangent line is always going to be horizontal because the line itself is horizontal. And so the slope of the tangent line is always 0. Hence, the derivative of the function at any point will be 0. We'll skip the limit definition proof because the visual proof probably is more important anyway. The next theorem says if we have a function that is of the form x to the n, so x squared, x to the fifth, x to the negative 2, x to the 1/3, those functions are differentiable, and the derivative pattern is you move the exponent down and make it a coefficient, and you subtract 1 from the exponent. Sometimes the differentiability at 0 depends, well, always, the differentiability at 0 depends on whether x to the n minus 1 is defined on an interval containing 0. But always, this is the pattern, and then sometimes we just have to worry about where is the function going to actually be differentiable. But this is the pattern we want to do anytime we have a function of x of the form x to the n. So let's take a look at a couple examples here. So the first one is, what is the derivative of x to the fifth? And we can see, well, that's this pattern, x to the n, where n is a rational number. And so we would say that's going to be 5x, move the exponent down, make it the coefficient, and then subtract 1 from the exponent to get the new exponent. So 5x to the fourth. Example 1b here looks like it might not exactly fit this pattern, but if we rewrite x1 over the cube root of x as x to the negative 1/3, then we can see, yes, this actually is that format x to the n where n is a rational number, so we can apply this power rule. Notice what I did was I rewrote the expression, but I did not yet take its derivative, so I still wrote the derivative of, and then I just rewrote what the function is whose derivative we're taking. So the derivative of x to the negative 1/3 is negative 1/3. I move the coefficient, or excuse me, the exponent down, turn it into the coefficient, and then make my new exponent 1 less. Negative 1/3 minus 1 is minus 3/3. So that's going to give me negative 4/3. So my new exponent is negative 4/3. And it's fine to leave it just like that. If you want to, you could rewrite it as negative 1, a 3 in the denominator. 4/3 is cube root of x to the fourth. The fourth power can go inside with the x, or you could have the cube root in parentheses and then a fourth power outside of that. Those are all the same thing. But it's certainly fine to just leave it as negative 1/3 times x to the negative 4/3. Right, so watch for those. Anytime you have a radical function like that, remember that that's just a power function in disguise. The next theorem says if I have a constant multiple of a function that is differentiable, then the constant multiple times our original function is also differentiable. And all we do is multiply the derivative of the original function by the constant multiple that we have. So if I have the derivative of 3 times the square root of x, I can say that's the same as 3 times the derivative of square root of x. And I might as well also recognize square root of x is x to the 1/2. And so then I just have this 3 times, and then I apply the power rule to the derivative of x to the 1/2. So I move the coefficient or exponent down, make it a coefficient, keep my x, and then my new exponent is 1/2 minus 1, so negative 1/2. And again, if you want to, you can rewrite that. The 3 would be in the numerator, 2 in the denominator, and x to the negative 1/2, that moves to the denominator as a square root of x. But it is fine to write just 3 times 1/2 times x to the negative 1/2. Just great to just leave it like that. And then example B, again, I want to rewrite g of t first as negative 4 times t to the negative 2. And so then when I do the derivative, I'm thinking I have a scalar multiple, so that just is brought along, and I have the scalar multiple times the derivative of t to the negative 2. The derivative of t to the negative 2, I can apply the power rule. So I'll have negative 2t, and then I subtract 1 from the exponent. Negative 2 minus 1 is negative 3. And then that, if I want to simplify it, I could multiply the negative 4 and the negative 2 together, and that's going to give me 8. T to the negative 3 is t to the third in the denominator. So you can see when I have just a scalar multiple or a constant multiple of another function, that multiple gets carried along, and then it's multiplied with the derivative of the other function. Notice that's different than if I just have a constant all by itself. If it's just a constant term not multiplied with something else, then the derivative for that would be 0. But when the constant is multiplied by another function, its derivative is not 0. We use the scalar times the derivative of the other function. All right, then we have what to do if we have the sum or difference of two functions that are differentiable. So if we have two functions that we know are differentiable and we add them or we subtract them, then the new function, the sum or the difference of the other two, is differentiable. And the derivative for the sum or difference is just the sum or difference of the derivatives. So let's use that together with our scalar multiple rule and the power rule that we've already talked about, and that's going to allow us to do the derivative for a polynomial. So something like this. Right, so we can say, well, this is the same as the derivative of 5x cubed minus the derivative of 3x squared plus the derivative of x minus the derivative of 4. And then we can say, well, I know here I have a scalar multiple times a power function. So the scalar multiple is multiplied by the derivative of the power function, which would be 3x squared, because I move the exponent down, make it a coefficient, and I subtract 1 from the exponent. And then the next term, I have something very similar. My scalar multiple stays there. And then I have times the derivative of x squared. And I'll move the exponent, make it a coefficient. And my new exponent would be 1, which I don't really need to write because x to the 1 is the same as x. Then I have the derivative of x. And we can use the power rule here. We'd say, well, the exponent is 1, so I'll move that down. And then I have x to the 0, but x to the 0 is just 1. So the derivative will just be 1. Or we could say, hey, that's linear, so the derivative is just the slope. So the derivative for that is 1. And then the last term, we have the derivative of a constant, and that will be 0. So let's simplify this a bit. We have 15x squared minus 6x plus 1 for the derivative of this function. The next example here involves a quotient, and we don't yet have the tools to work with a quotient. So the first thing we need to do is get this into something that just looks like a sum or difference of terms we can differentiate. So let's think about this. If I have a quotient where there's just one term in the denominator, I can rewrite each of these as a fraction. 3 times t to the 5th divided by t squared plus 4t squared over t squared minus 7t over t squared plus 6 over t squared. And then I can get each of those terms into something that looks like a constant multiple and a power function. So here we'd have 3t cubed, and then these we would have t squared over t squared will reduce to 1, so just 4. And then the next one will have 7 times 1 over t, which I'm going to rewrite as t to the negative 1. And then the last one I'll rewrite as 6 times t to the negative 2. Notice at that step I carried the d dt along because I have not yet taken the derivative, but now I'm going to take the derivative, so it's no longer the derivative of something, it actually is the derivative itself. So we'll have the scalar multiple times the derivative of t cubed, which will be 3t squared. Move the exponent down and subtract 1 from the exponent. The derivative of a constant term like that is 0. And then we'll take the 7, that's the scalar multiple, times the derivative of t to the negative 1. Move the exponent down and subtract 1 from the exponent. Negative 1 minus 1 is negative 2. And then same on the last one, we carry our 6 along, scalar multiple of the derivative of t to the negative 2. So negative 2, t to the negative 3. And then we can clean this up a bit. We have 9t squared plus 0, we'll leave that off, plus 7 divided by t squared. And then it looks like minus 12 over t cubed. So we needed to do some rewriting of the function whose derivative we were taking before we were able to actually compute the derivative. All right, in example 4, we have a function that represents the position of a particle moving along a straight line, and the input is seconds and the output is inches, and we're looking for the velocity of the particle at t equals 0 and also at t equals 2. So it's probably helpful to just find the velocity at any time first and then put in the values of t equals 0 and t equals 2 specifically. So we remember that the velocity is the first derivative of position, and here the position was given as an h of t, so we'll write v of t is h prime of t, and we can see that this function is a power function, 2 power functions, so a polynomial. So we have the derivative would be 3t squared, and then we bring along the scalar multiple. The derivative of t squared would be 2t to the 1, or just 2t. So the velocity at 0 seconds will be 3 times 0 squared minus 0. So 0, and let's see, we would have inches per second. And the velocity at 2 seconds looks like it will be 3 times 2 squared minus 2. So 12 minus 2, so 10 inches per second. Example 5 asks us to find the equation of the tangent line to the graph of this function at x equals 2. Remember, when we want equations of tangent lines, our pattern was y equals the derivative at our point A times the change in x, so x minus a, plus the y value at our point a, f of a. So this is the structure we want. So we need to figure out first that this is our a value. A equals 2 is our anchor point. And let's see, f of a is going to be 3 times 2 squared minus 11. So let's see, that's 12 minus 11, so 1. And our derivative, first we can find f prime of x, and then we'll fill in x equals 2. So first we want to find the derivative at any point, which looks like it will be 3 times 2x minus 0. So that will make 6x. And that means the derivative at 2 will be 12. So the equation of the tangent line will be y equals 12 will be the slope, x minus 2 plus 1. And if we want to, we can rewrite that as y equals 12x minus 24, and then plus 1, so y equals 12x minus 23. So I would say, why don't you grab your calculator and let's plot the function and the tangent line and make sure it looks the way we want it to look. So our function was 3x squared minus 11, and our tangent line was 12x minus 23. And the tangent point we were looking at was x equals 2 and y equals 1. So I have a picture here. It looks like that could certainly be the tangent line at 2, 1. Yep, looks good. Next, we will talk about how to deal with functions that are the product of two other functions, or functions that involve a couple of factors. The rule says the derivative of the product of two functions is the first factor left just as it is times the derivative of the second factor plus the second factor left just as it is times the derivative of the first factor. So first times the derivative of the second plus second times the derivative of the first. So if we have this function in example 6, h of x equals the group x cubed minus 4x times the group 7x squared plus 5, and we want to find the derivative using the product rule, we'll say we want to find h prime of x, and to do so we're going to first leave the first factor the same, and then multiply by the derivative of the second factor. The derivative of the second factor will be 7 times the derivative of x squared, which is 2x, plus the derivative of 5, which is 0, because that's a constant term. So far we have the first factor times the derivative of the second factor, and now we want plus the second factor times the derivative of the first factor. And for that we'll do 3x, and then we'll subtract 1 from the exponent, so 3x squared minus the derivative of 4x is just 4, because that is a linear function, 4x, and the derivative for a linear function is just the slope of that function. Or you can think there's an exponent 1, so I'll bring that down and multiply by the 4, x to the 0 is just 1. But to me, it's a lot easier to just think the derivative for a linear function is the slope of the function, or the coefficient on x. So there we have the derivative, and typically I would say just leave it in that form, but what I want to do is compare what we would get if we find the derivative without the product rule. And so I do want to simplify this so that we can compare the results. So let's go ahead and expand here. I'm going to multiply everything by, or distribute this 14x. So I'll have 14x to the fourth. Let's see. minus 56x squared plus 21x to the fourth minus 28x squared plus 15x squared minus 20. And if I combine like terms, I have, let's see, 35x to the fourth. Let's see, if I combine these two, I have minus 84x squared. Negative 84 plus 15 is minus 69x squared, and then I have minus 20. So there's our simplified version of h prime. And then let's see what we compare that with what we get if we don't use the product rule. If we're not going to use product rule, we need to instead rewrite h of x before differentiating, because as it is, there are factors involved, so we would need the product rule. But if we want to avoid using the product rule, we can expand h as a first step. If we do that and FOIL, we'll have 7x to the fifth minus 28x cubed plus 5x cubed minus 20x. So that's h of x equals 7x to the fifth. Let's see, minus 23 x cubed minus 20x. Now we have h written in a form where we wouldn't need the product rule, so we can differentiate just using sum and difference rules and this constant multiple rule. So we would have 7 times the derivative of x to the fifth, which is 5x to the fourth, minus 23 times the derivative of x cubed, which is 3x squared, minus the derivative of 20x, which is just 20. So h prime of x, taking this route, we get 35 x to the fourth minus 69x squared minus 20. Thankfully, same as we got using the product rule. So we can take either approach. It's just whether we want to do the work of rewriting h before we do the derivative, or whether we'd like to use the product rule. Typically, when we have a product, it's just going to be faster to use the product rule. In example 7, we really wouldn't want to think about expanding this and then differentiating. It'll be much easier to just use the product rule. So again, you see we have the product of two factors. So if I want to find the derivative, instead of writing g prime of t, they're asking us to write dg dt, but remember that's just same notation, or different notation, but for the same process for finding the derivative with respect to t. And again, we see we have a product, so we want the first factor left just as it is, times the derivative of the second factor. It's going to help us quite a bit to rewrite g itself so that we can see what the powers are on t. So that first factor would be t to the 1/3 times 4 plus t squared. And then the second factor, remember when there's a t in the denominator, that's the same as t to the negative 1. So I could rewrite that as 2t to the negative 1 minus 4t to the 2.3. So there's g just rewritten. And now when I do the derivative of the second factor, I think, okay, I have my 2 constant multiple, and then I bring down the exponent, and I subtract 1 from the old exponent, and that becomes my new exponent. Negative 1 minus 1 is negative 2. And then I say I have my constant multiple 4, bring down the exponent, that's 2.3, and subtract 1 from the exponent, that's 1.3 as the new exponent. So there's the first times the derivative of the second, and then I want to add to that the second times the derivative of the first. The derivative of the first will look like 2t plus 4 times the exponent on t, which was 1/3, not 1/2, times t, and the new exponent will be 1/3 minus 1, so 1/3 minus 3/3 is negative 2/3. So it's completely fine to leave the derivative like that, just for the refresher on rewriting things back into the form where they kind of started. Let's leave the factors, but rewrite radicals as radicals and put negative exponents back down as positive exponents in the denominator. So 2 times negative 1, t to the negative 2, that's the same as negative 2 in the numerator over t squared in the denominator. And then the next term here, I would multiply the 4 times 2.3. That's going to give me, what, 9.2 times t to the 1.3. And then we have our 2 over t minus 4t to the 2.3. And the next factor, we could rewrite that second term as 4 would stay in the numerator, 3 is in the denominator, along with the cube root of t squared. Since that exponent is negative, it moves to the denominator. The 3 in the denominator of the exponent tells me I have a cube root, and the 2 in the numerator of the exponent tells me I want a t squared inside that cube root. So either of those is fine. I just want to help you remember how to move back and forth between exponents and radicals and between negative and positive exponents. Then we have the quotient rule, which tells us how to deal with the derivative or find the derivative of a function that is the ratio of two other functions. And so it says we will have, if we're looking at the ratio of two functions, the way to find the derivative is leave the first factor in the numerator alone, and that's coming from the denominator of your original function. So multiply the denominator of the original function by the derivative of the numerator. Subtract from that the numerator of the original function times the derivative of the denominator, and divide that by the denominator of the original function squared. And this is only good when the denominator is not 0. Of course, we always have to watch for the denominators being 0. Typically, people remember this mnemonic, low d high minus high d low divided by low squared. So anywhere you have the d, you think of that as derivative of. So low would be your denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So again, low d high minus high d low over low squared. So in example 8, we notice that y is a ratio of two functions, or a quotient of two functions. And so in order to evaluate this derivative, we need the quotient rule. So in the way I've written this here, low would be x to the 4th plus 5, and high would be 3 minus 4x. So when I write d low, that's 4x cubed, and when I write d high, that would be negative 4, right from the derivative of the numerator or the derivative of the denominator. Derivative of the denominator for d low, derivative of the numerator for d high. So when I put these pieces together, I would say dy dx, low was x to the 4th plus 5, d high is negative 4. I'll try to remember to be consistent with writing my derivatives in a different color, minus high d low divided by low squared. So the denominator here, we don't do the derivative of the denominator, we just take the original denominator and we square it. So let's spend a little time cleaning that up. That would be negative 4x to the fourth minus 20 minus 12x cubed plus 16x to the fourth over x to the fourth plus 5 squared. And if we combine some like terms there, we'd have 12x to the fourth minus 12x cubed minus 20 over x to the fourth plus 5 squared. I'm not going to have you worry too much when our goal is just to find the derivative. I'm not going to worry too much about having a simplified form, but sometimes our goal is going to be actually to do something with the derivative. So there are going to be times when we need to use a simplified form. So I'm going to work through these to get a nicer form, just so I'm demonstrating the habits of getting to that cleaner form. But on a quiz or an exam, if I'm asking for just the derivative, you can leave it after that first step where you've put all the pieces together and you haven't simplified them. That's just fine. All right, example 9. Again, we have a quotient of two functions, and we're asked to find not just the first derivative, but also the second derivative. So let's go for it. So we'd say we need the quotient rule. So we're doing low times the derivative of the high, low d high, minus high d low divided by low squared. And maybe it helps to write those over here. High is x to the fifth plus 3x cubed minus 4. So d high, the derivative of the numerator, will be 5x to the fourth minus 3 times 3x squared minus 0. And low, the denominator, will be x squared plus 2. And d low, the derivative of the denominator, will be 2x. So putting those pieces together, we'll have f prime of x is low, which we had as x squared plus 2, d high, that's 5x to the fourth. I have a sign error there, that should be plus 9x squared. And the derivative of that negative 4 is just 0, so that's it for the derivative of the numerator. And then we want minus high, which was x to the fifth, plus 3x cubed minus 4, and d low, which was 2x. And we want that all divided by the denominator squared. I'm not going to simplify this one. I'm sure that you could do the process if you need to. Actually, I just should have looked ahead and I forgot that we needed to find f double prime. Anytime we want to find the second derivative, it is worth the effort to simplify the first derivative. So let's go ahead and do that. So on the first group in the numerator, I need to FOIL. So I've got 5x to the sixth plus 10x to the fourth plus 9x to the fourth plus 9x squared. And in the second group, I'm really just distributing that 2x. So minus, I'm going to distribute the subtraction after I distribute the 2x. So I'd have minus, let's see, 2x to the sixth plus 6x to the fourth minus 8x. And then in the denominator, I'm just going to leave this as x squared plus 2 squared. Nope, I'm going to expand that too, because we need to take its derivative, and so we're going to need it in expanded form. Let's see, so if I expand that, that's going to be x to the fourth plus 4x squared plus 4. Okay, so we'll keep simplifying f prime. In the numerator, I can see I'm going to have 5x to the 6th minus 2x to the 6th, so that's 3x to the 6th. X to the 4th I have from the first group here 19, and then I need to subtract 6. So 19 minus 6, that's 13, x to the 4th. And I have plus 9x squared, and it looks like plus 8x. And the denominator, again, I'll just rewrite x to the 4th plus 4x squared plus 4. And now for the second derivative, I need the quotient rule again, because I'm just taking the derivative of the first derivative. So I just restart and I say, okay, now high is 3x to the 6th plus 13x to the 4th plus 19 plus 9x squared plus 8x. So the derivative of the numerator will be 3 times 6, so 18x to the 5th when I subtract 1 from the exponent, plus 13 times 4, so let's see, that's 52x cubed, plus 9 times 2, that's 18, x to the 1, plus 8 for the derivative of 8x. Then the denominator, low, will be x to the 4th plus 4x squared plus 4. So d low will be 4x cubed plus 4 times 2, so that's 8x to the 1, and the derivative of 4 is 0. Then if we put those pieces together, we have high d low minus low d high divided by low squared. So last step, just write that denominator again with a square. So again, anytime you need to do a second derivative of a function, it will help to clean it up as much as you can before doing the derivative, that next step. Example 10 and 11 are a little bit different because we don't have specific formulas for functions. In 11, we have the graphs of some functions, and example 10, we have a function that's made up of 2 other functions. So we're assuming that h and g are functions we don't know, but they're differentiable. So let's write that. Assume h of x and g of x are differentiable. And that k is a combination of those functions and also the scalar multiple 3 or the constant multiple 3 and the function x squared. So if I want to find the derivative for k, it's going to involve the derivatives of these other functions. But I can think, well, k is a constant multiple of one function, and when I do the derivative of a constant multiple of a function, I just keep that constant multiple and multiply it by the derivative of the function it's multiplied by. So in this case, that would be h prime of x. I don't need the product rule there because only one of those factors involves a variable. So in this case, rather than using the product rule, I'm just using the constant multiple rule. So I do 3 times the derivative of h. And then I will add to that the derivative of x squared times g of x. When I do the derivative of this term, this will require product rule, because there I have two factors that both involve a variable. So when I do the derivative of that, I'm going to say it's the first, left as it is, times the derivative of the second, but I don't know what g is, so I just have to write g prime for the derivative of the second. Then I want to add the second factor left as it is times the derivative of the first factor, so times the derivative of x squared, which is just 2x. So we don't have a specific formula, but we're showing here's how I would find the derivative of k if I know the derivatives of those other functions. And that's what this kind of problem is asking us to do. Example 11, we have the graph of a function f that looks like kind of a piecewise function, and the graph of a function g that looks like either a piecewise function or a transformed absolute value function. It looks like it's probably piecewise because we have different slopes on the two sides of that vertex point. And so the first question here is asking us to find the derivative of f times g at 2, right? And we can see this is a product of two functions. So the derivative involves the product rule. And we think, well, the product rule says I want the first function times the derivative of the second function plus the second function times the derivative of the first. Anytime I have function values, I want just the y-coordinates from the graph. And anytime I have a derivative, I want the slope from the graph. So function values, those are y-coordinates. Derivative values are slopes of tangent lines, but in most cases here, that's just going to be the slope, because most of these pieces are just linear. Okay, so we want y-coordinates for these two, and we want the slopes of the tangent lines for these two. So the y-coordinate of f when x is 2, that appears to be 3. And the y-coordinate of g when x is 2, that appears to be 2. So I've got my function values, and now I need the slopes. The slope of g when x is 2, if I'm looking at this graph correctly, it looks like it's a half because I'm going up 1 and over 2 for that line. So g prime of 2 is going to be a half. F prime at 2 appears to be 0 because that's a low point on that graph, and the tangent line there appears to be horizontal. So f prime of 2, I'm going to fill in 0 since it looks like I have a horizontal tangent line there. So putting those factors together and then adding them, I've got 3 halves plus 0, so 3 halves, as the derivative for the product function f times g at 2. So what you'll notice is I don't need to sketch that product function. I just use the pieces that I would get from using the product rule for the derivative, and then I take those pieces from the individual graphs of f and g. Similarly, if I have the new function f divided by g, and I want to find its derivative, I am going to need the quotient rule. which says the derivative for this quotient at a point is low, the denominator at that point, times d high, the derivative of the numerator at that point, minus high d low divided by low squared. Not the derivative, just the function value squared. So again, some of these are going to be y-coordinates. This will be a y-coordinate, and this will be a y-coordinate, and that will be a y-coordinate. And some will be slopes of tangent lines, anywhere we need a derivative value. So the y-coordinate from G at 7 looks like that's 1. So that is filled in the numerator and also in the denominator. The y-coordinate from F at 7 is 5. And then we want to fill in the slopes. The slope of F at 7 is just whatever the slope of that line is. And I can count from this point to this point, and I'm seeing I go down 2 and right 3. So that slope would be negative 2/3. Oh, that's the wrong function. That's the derivative for G. So let's move that over here. That was the correct slope, but for G, so negative 2/3 there. And the derivative for F, now I want to look at the graph of F and figure out the slope of that function. It looks like I'm going up 1 and right 4, so 1/4 for that. And then doing those computations, I have a 1/4 plus 10/3 divided by 1. So if I want to, I can get a common denominator of 12 here. So multiply this one by 3/3, that's 12, nope, 3/12. And multiply the second by 4/4, that's 40/12. So I should get 43/12. So that example is just a little bit different because, again, we don't have formulas for these functions. We could create them, but we don't need to do these computations. We really just need to grab some y values and slopes from the graph. All right, then the next thing we want to talk about is if we want to find locations of horizontal tangent lines. What you want to remember is that a horizontal line has slope 0. So if I want to find the locations of horizontal tangent lines, I will find the derivative, because the derivative tells me the slope of the tangent line, set f prime equal to 0 after I find it, and solve for x. And then if we need the y-coordinates, to find the y-coordinates, we use f of x always, not the derivative, right? The derivative tells us the slopes of the tangent lines. The y-coordinates are always coming from the original function. So if we're asked to find all points on the graph of this function that's given where the tangent line is horizontal, we will follow that process and we'll say, first, I need to know what is the function that gives me the slope of the tangent line at any point. And for this, we'll have 3x squared plus 2x minus 1 from the slope of negative x, and then minus 0 for the derivative of negative 1. Right, and the tangent line is horizontal when the derivative is 0. So we want to set this equal to 0 and solve for x. Let's hope that we can factor this. Must be 3x and x. And it would have to be 1 and -1 to get a -1 on the end. Let's see if we do +1 here and a -1 there. That'll give us 3x squared plus 3x minus x. Yep, that works. So that tells me either x is a third to make the first factor 0, or x is -1 to make the second factor 0. So the points at which the tangent line is horizontal would be 1/3 and then f of 1/3 to find the y-coordinate, and -1 f of -1 to find the y-coordinate. So let's see, if we put 1/3 into f, we'll have 1/27 plus 1/9 minus a third minus 1. I'm just going to write that. And you could compute that fraction. I'm just going to leave it like that, just emphasizing that you'll put the x back into the original function. And for the other one, we'll have -1 as the x, and then let's see, -1 plus 1 plus 1 again minus 1. So that ends up to be 0 as the y-coordinate. And again, that's just coincidental. It doesn't usually come out to be the same as the slope of the tangent line, right? But we would set the derivative equal to 0, find those x coordinates, and then use those x coordinates in the original function to find the y coordinates. Right? Let's take a look at this graph just to see how this is looking. So you grab GeoGebra or your graphing calculator. This function was x cubed plus x squared x cubed plus x squared minus x minus 1, right? And we came up with the horizontal tangent lines occurring at -1, 0, that's good. And then 1/3, and we don't know what f of 1/3 is, but let's just have the calculator compute that for us. F of 1/3. So let's see if it'll give it to us as a fraction. It won't, but roughly -1.185. So it's certainly going to be a fraction with a denominator of 27 probably, but looks like our work makes sense, right? We have this point at x equals -1 where we have a horizontal tangent line where the graph hits a high point, and we have a horizontal tangent line again when x is when x is a third when that function hits a low point. Okay, then the next example is similar. Get out of that. Okay, find the points at which the line tangent to the graph of this function f is parallel to the line y equals 2x plus 3. Remember, parallel lines have the same slope. So we want the derivative to be the same as the slope of this line because we want them to be parallel. So we want the derivative to be 2 from the slope of 2x plus 3. Remember, the derivative gives us the slopes of the tangent lines, and we want our tangent line to be parallel to the given line, so we want our derivative to be 2. So this is going to be a very similar process to the last problem, but instead of looking for a horizontal tangent line, we're looking for a place where the tangent line has a slope 2 rather than slope 0. So we'll find the derivative because that tells us the slope of the tangent line at any given point. And the derivative will be 4 times 2, so 8x to the 1 minus 3 from the derivative of 3x plus 0 from the derivative of 2. So that's the derivative at any point, right? And we want to know where the function is parallel to 2x plus 3. So where is the derivative equal to 2? So that's our question, and that would mean 8x minus 3 is equal to 2. And so we say, well, that's going to happen at, let's see, 8x equals 5. So x equals 5/8. And it says find the points, both the x and the y coordinate. So the y coordinate would be f of 5/8. So 4 times 5/8 squared minus 3 times 5/8 plus 2. So let's see, let's go ahead and do this. So we'd have 4 times 25 over 64 minus 15 over 8 plus 2. That gives me, let's see, 4 over 64 I can reduce. That's the same as 1 over 16. So 25 over 16 minus 15 over 8. I want to get a common denominator there, so that's 30 over 16. And 2 is 32 over 16. So let's see, we've got a common denominator all the way through. 25 minus 30, that's -5. -5 plus 32 is 27. So 27 over 16. So the point we are looking for is, if we did this correctly, 5/8, 27/16. So let's take a look at these graphs and see if it looks good. So now we want to turn those off, and we want to graph 4x squared minus 3x plus 2. And I want to graph the line 2x plus 3. Right? And I want to figure out, does it look like at the point 5/8, 27/16 that we have a tangent line that's parallel to that line 2x plus 3. Let's find the equation of the tangent line at this point. If we've done this correctly. It wasn't part of the problem, but it will help us for our checking on the graph. So for equations of tangent lines, we do y equals the derivative, which we think is supposed to be 2, x minus the x coordinate plus the y coordinate. So if we've done everything correctly, it's going to look like the tangent line at that point 5/8, 27/16 that we just built is parallel to this line. They're going to be parallel, and it's just a question of, does this actually look like the tangent line? So let's do this. 2 times x minus 5/8. And then we want plus 27/16. It looks good, right? It looks like we have a line here that's tangent to the graph at the point we're interested in, and it looks like it's certainly parallel to that other line. So it's believable that our work was correct. Then our last example says find a quadratic polynomial such that f of 1 is 5, f prime at 1 is 3, and f double prime at 1 is 6. So all we're told is that we're looking for a quadratic polynomial. So we know only that the function is of the form ax squared plus bx plus c. So we have three unknowns. We don't know A, we don't know B, and we don't know C. But luckily, we have three pieces of information. So we should be able to use those three pieces of information to find our three unknowns, these parameters A and B and C, right? To build the polynomial that goes through the point 1, 5, that has its first derivative being 3 when x is 1, and its second derivative being 6 when x is 1. So think of A and B and C as constants that we just don't know. So think of A and B and C as unknown constants. So when we do derivatives, we'll treat them as if they were a 7 or a 2 or a 3. Even though they look like variables, we'll treat them as just constants. So our formula for f prime, we're thinking that's going to be a, because that's a constant multiple of x squared, times the derivative of x squared, which is 2x. And we would think the derivative of bx is just like the derivative of 7x would be 7. The derivative of bx will just be b. And just like the derivative of 5 would be 0, the derivative of c will be 0 because c is a constant. Let's rewrite that so it just looks more conventional. That's 2a times x plus b for the derivative. And for the second derivative, we'll keep using the same idea. Now I have 2a times x. So 2a is just a constant multiple of x. A derivative for the constant multiple of x is just whatever that coefficient is. So 2a. And the derivative for b is just 0 because b is a constant term. So what we have is the derivative, or the function itself, is ax squared plus bx plus c. The derivative is 2ax, and the second derivative is 2a. Now notice the second derivative doesn't involve x. So, knowing that the second derivative at 1 is 6, that tells us what 2a is, right? We need f double prime at 1 to be 6. That means 2a has to be 6 because the second derivative at every point is 6. So specifically, a is going to be 3. Right? So now we know that a is 3, we can update the other two, and we can say now the second derivative is actually 6x, right? And we need the second derivative at 1 to be 3. Excuse me, the first derivative at 1 to be 3. So that's going to be 6 times 1 equals 3. I just messed something up here. Let me see what I did. The first derivative was supposed to be 2ax plus b. Okay, there we go. So we actually need 6x plus b. This wasn't going to work, right? 6 was not going to be 3. So let's clean that up a little bit. So again, the first place I made a mistake was when I recopied the first derivative. I just wrote down 2ax. It should have been 2ax plus b. That did not have an impact on what a was, but when I wrote down the first derivative down here, we needed 6x plus b rather than just 6x, right? So 6x plus b, and we need the derivative at 1 to be 3. So 6 times 1 plus b needs to be 3. That tells me b has to be negative 3, 3 minus 6. And now I can update my original function And now I know that f of x is ax squared, so 3x squared, filling in that a value, plus bx, but b was negative 3, so negative 3x plus c, right? And now we still need to figure out what c is, but we're told that f of 1 is 5. And that's the piece of information we haven't used yet. So if I fill in x equals 1, I have 3 times 1 squared minus 3 times 1 plus c is 5. So that tells me 3 minus 3 plus c is 5. And 3 minus 3 is 0, so this just gives me c is 5. And now we have all the pieces we were missing at the start. We didn't know a and b and c, and now we know all three of them. And so our answer would be f of x is the function 3x squared minus 3x plus 5. And you can double check that function will have the correct function value and the correct derivative value and the correct second derivative value when x is 1.